Okay, this is the index. 1. The first topic is measurement fundamentals, analog signal standards, milliamps and volt, smart protocols, HART, foundation, Fieldbus, Profibus PA, temperature, RTDs, vs thermocouples, pressure, gauge absolute differential, flow basics and Reynolds number, orifice plates, and DP primary elements. 8. Coriolis mass flow method. 9. Magnetic vortex and ultrasonic flow. 10. Level, hydrostatic, radar, ultrasonic. 11. Point level, switches and safeties. pH and ORP measurement, conductivity and resistivity, gas analyzers, O2, CO, CO2, H2S, process gas chromatographs, sampling systems, control valves, treatment characteristics, actuators and positioners, cavitation, flashing and noise, loop fundamentals, PID, advanced control, cascade, feedforward, split range. 22. Signal conditioning and filtering. 23. Scaling, ranging, LRB, URB. 24. Marshalling, IO, and wiring. 25. Grounding, shielding, and noise. 26. Power supplies and redundancy. 27. Hazardous areas and protection concepts. 28. SIS, seal, test, loop checks. Commissioning, factory acceptance test, site acceptance test, loop checks. 32. Troubleshooting playbook. 33. Material compatibility and weighted parts. 34. Environmental ratings and enclosures. 35. Wireless instrumentation, wireless HART, ISA 100. 36. Digital communication, Modbus, Ethernet IP, Profinet. 37. Asset management systems. 38. Impulse lines and manifolds. 39. Diaphragm seals and remote seals. 40. Square root vs linear extraction. 41. Alarm management, custody transfer and flow computers, vibration and machinery monitoring. 44. Hydrocarbon detection and FGS. 45. H2S measurement and safety. 46. Instrumentation in skids, separator, compressor, metering. 47. PLC, DCS, interface basics. 48. Human-machine interface. 4 instruments. 49. Maintenance strategies. 50. Documentation and change control. 51. Cybersecurity for instrumentation. 52. Common field mistakes to avoid. 53. Checklist pre-startup essential. 54. Career practice from tech to engineer. Okay, so instrumentation to practical instrumentation study guide. This instrumentation is the nervous system of modern industry. Every process plant, whether in oil and gas, power generation, water treatment, or manufacturing, relies on accurate, reliable measurements and controls to operate safely, efficiently, and profitably. This course is designed to give engineers across 54 structured topics. You will learn how to measure key process variables like pressure, flow, temperature, level, pH, and gas composition. Transmit and interpret signals from classic 420 milliamps loops to modern digital protocols like HART, Fieldbus, and Ethernet-based networks. Control processes using valves, actuators, and control strategies, PID cascades, feedforward. Maintain and troubleshoot systems through calibration, diagnostics, and asset management tools. Ensure safety and compliance in hazardous areas, seal-rated systems, and custody transfer. Develop professional practice from commissioning checklists to documentation discipline and career growth from technician to engineer. The study guide is concise but actionable. Each topic is explained in a compact 5 sentence form, supported with real-world examples from oil and gas, electrical and instrumentation, automation, PLC DCS, and commissioning work. The intent is not just to pass on knowledge, but to provide a ready reference for daily field challenges, something you can revisit before shift, during troubleshooting, or while preparing for an interview. By the end of this course, you will have a strong foundation in instrumentation principles, the ability to apply concepts directly in fieldwork and projects, a structured knowledge base that supports career growth from field technician to instrumentation or automation engineer. This is not purely academic guide, it's a practical toolbox designed for professionals who want to learn quickly, revise effectively, and apply confidently in real plans and projects. So let's start with the first topic, measurement fundamentals. Instrumentation turns physical phenomena into standardized signals. A good measurement is accurate, repeatable, and traceable to a standard. Range, resolution, linearity, and uncertainty define what the reading truly means. Errors stack from sensors, wiring, transmitter, scaling, and software. Always ask what is the process variables and record accuracy at operating conditions. So, the measurement is the bridge between reality and control, converting a temperature, pressure, level or flow into a standardized electrical digital value that people and control system can act on. A useful measurement has known accuracy, repeatability. Can you get the same result repeatedly under same conditions? And traceability, calibrated against a standard with certificate. Practical factors, sensor range selection, resolution, linearity, heuristic, and uncertainty all affect whether the reading is good enough for control or custody transfer. Errors are cumulative. A small sensor offset plus wiring drop plus transmitter rounding plus scaling error in PLC can create a significant final error. Always do end-to-end checks. Example, when you select a pressure transmitter for separator, choose a span where normal operation sits at 20 to 80% of range to maximize resolution and reduce relative uncertainty. Analog signal standards. Milliamps, current or voltage. The 420 milliamps loop is dominant because it rejects noise and detects open circuits. 125 volt is used for short runs and inside cabinet. A voltage drop matter over distance. Loop power, burden resistance, and intrinsically safety barriers affect signal headroom. Scale saw LRV maps to 4 milliamps and URV to 20 milliamps. Documenting units and engineering range. Use shielded twisted pair, single point to point, single point grounding, and avoid shading returns. The 4 to 20 milliamps wires the field because its current loop aiming to voltage drops and allows live detection of open circuits. 0 milliamps fault. The voltage signals, example 0 to 10 volts or 1 to 5, are fine inside the cabinet or short lanes but suffer from cable drop and require attention to input impedance. Remember, loop power and burden resistance. A transmitter's brick must see enough headroom across barriers, isolators, or long cables. Always document LRV, URV, and engineering units, and wire with shielded twisted pair, single point ground, the shield unless IS wiring prescribes otherwise. Example, when connecting a transmitter through an intrinsically safety barrier, verify the barrier's maximum load resistance so the transmitter still sees 4 milliamps at LRV. Smart protocols. HART, Foundation Fieldbus, Profibus PA. HART overlays digital communication on the 420 milliamp signal for configuration and diagnostics. Foundation Fieldbus and Profibus PA are fully digital, powering devices and carrying cyclic data. Function blocks in FF enable control in the field for deterministic behavior. Device descriptors DD, EDD, and FDT DTM packages enable rich configuration UIs. Keep a current device database and backups for turnarounds. HART lets you keep the 420 milliamps primary loop while overlaying low-speed digital channel for device config and diagnostics. great for incremental upgrades. Fieldbus FF and Profibus PA are full digital channels. They can power field devices, carry cyclic data, and allow function block control in the field, enabling distributed control strategies. Device descriptors DDEDD and FDT-DTM abstract device specifics for consistent engineering tools. Maintain a device library and backups before turnaround. Use the digital diagnostics to trend the device health, zero drift valve trouble, and set predictive maintenance work orders. Example: use HART diagnostics to spot a transmitter with increased noise elements before it fails, and schedule replacement during planned turnarounds. Temperature: RTDs, PRs, thermocouples. RTDs PT100, PT1000 are accurate and stable, but limited to 600 degrees Celsius. Thermocouples cover wide ranges and fast response, but need cold junction compensation. 3-wire, 4-wire RTD wiring cancels lead resistance. Keep lead lengths balanced. Use proper sheath insertion depth and thermal paste for representative readings. Calibrate in the accurate axial range and verify drift after thermal cycles. RTDs PT100, PT1000 offer high stability and accuracy in moderate temperatures. Thermocouples cover extreme ranges and transient response. Use 3 or 4-wire RTD wiring to cancel lead resistance, keep length balanced, and use proper terminal block wiring. Thermocouples need a cold junction compensation and shielding from EM noise. Choose appropriate sheet materials and ensure adequate immersion depth. Calibrate sensors in the actual process range and confirm drift after thermal cycling. Example: for furnace control to 900 degrees Celsius, choose a Type K thermocouple with ceramic insulated extension to the thermocouple transmitter, not an RTD. Pressure, gauge, absolute, differential. Gauge pressure references atmosphere. Absolute uses a sealed vacuum. Differential measures between 2 points. DP transmitters with orifices or pitot tubes overflow via delta P proportional to velocity. For level in pressurized vessels, DP uses wet or dry legs, condensate spots, stabilize steam legs. Use diaphragm seals for corrosive, viscous, or plug-in services. Mount to minimize head effects and impulse line errors. Gauge pressure reads relative to atmospheric pressure. Good for process tanks. Absolute pressure is needed for vacuum or when barometric variations matter. Differential transmitters measure delta P between 2 points. Used for flow, filter monitoring, and level in pressurized vessels. In steam service, use condensate pots, seal wet legs, or dry legs to avoid false readings. For corrosive fluids, use diaphragm seals, mount impulse lines to avoid traps, and ensure proper drain venting. Example: Level measurement on pressurized separator. Use a DP transmitter with field remote seal on the high side and vent low side reference to avoid gas pockets. Flow basics and Reynolds numbers. Differential devices need sufficient straight run and beta ratio selection. Volumetric vs mass flow matters for compensation and custody transfer. Always validate process conditions via meter turn down. Reynolds number indicates whether flow is laminar or turbulent. This determines which meters will perform well and what straight run is required for DP-based meters. Orifice, Venturi, a sufficient Reynolds and the straight run maintain predictable profile. Mass flow, Coriolis vs volumetric flow, magnetic or turbine matters for density compensation needs. Custody transfer often requires mass or compensated volumetric flow. Validate that process run stays within meter turn down. Many meters lose accuracy at extreme low flows. Example, if a pipeline's viscosity increases due to heavy crude, Reynolds drops. A vortex meter that worked previously may fall into transitional flow and lose accuracy. Orifice plates and DP primary elements. Orifice, venturi, nozzle, and wedge elements create a predictable pressure drop. Accuracy depends on plate bore, sharpness, centering, and upstream-downstream straight length. Square root extraction converts delta P to flow. Do it once, transmitters, or DCS. Not twice. Condensation, plugging, and pulsation degrade signals. Use filters and proper tabs. Inspect plates during shutdown and document tag bore reorientation. Orifice plates create a delta P that scales with velocity scale. Manufacturing tolerances, centering, and edge sharpness matter for accuracy. The beta ratio selection and minimum upstream thread pipe are critical for repeatable results. When using square section, do it once. Preferability in transmitters to avoid double processing errors. Protect orifice tabs from condensation and pulsation. Coriolis mass flow meters. Coriolis meters directly measure mass flow by detecting tube vibration phase shift. They also provide density and temperature, enabling concentration estimates. They are robust to profile but sensitive to two-phase flow and entrained gas. Ensure proper support to avoid external vibration coupling. Zero the meter under no flow. Full liquid conditions for best accuracy. Coriolis meters measure mass flow by detecting phase or time shift in vibrated tubes and often report density and temperature too. They excel for direct mass-based custody transfer and concentration measurement, but are sensitive to entrained gas or two-phase flow, which decouple the tube's vibration. Support piping firmly and follow manufacturer's recommendations for straight run and monitoring to avoid vibration crosstalk. Always zero. Nail the meter with clean liquid no flow conditions to establish a baseline. Example: for dosing a chemical by mass to a pipeline, a Coriolis eliminates density compensation math and improves accuracy via volumetric metering. Magnetic, vortex, and ultrasonic flow. Magnetars require conductive fluids and provide low pressure drop with good accuracy. Vortex meters exploit von Karman vortex shielding. They need stable Reynolds and straight run. Transit time ultrasonic measures velocity from time of flight differences. Doppler works with particulates bubbles. Clamp-on ultrasonics enable non-intrusive checks and temporary metering. Choose based on fluid cleanliness and maintenance constraints. Magnetars require conductive fluid. They offer near zero pressure drop and wide ranges for slurries. Vortex meters use vortex shielding and need stable Reynolds numbers with straight runs. Transit time ultrasonic time of flight works for clean fluids. Doppler ultrasonic works with entrained particles or bubbles. Clampon ultrasonic offers non-intrusive verification but typically lower accuracy than inline meters. Example: choose magmeter for wastewater with solids. Use Clampon ultrasound for temporary verification during commissioning. Level hydrostatic radar ultrasonic. Hydrostatic level converts head pressure to high. Density changes must be considered. A guided wave radar works in vapors and narrow nozzles. Free space radar handles most conditions with proper image. Ultrasonic is cost effective but affected by temperature and vapors. Used for simple tanks, bypass spreader installations, ease maintenance, stealing where stabilize surface. Validate against deep measurements and document reference data. Hydrostatic level uses head pressure if density varies in temperature composition. It must be compensated. Guide wave radars works in vapors and narrow nozzles and is great for interface stratified fluids. Free space radar is ideal for tall tanks where aiming and the blind zones are managed. Ultrasonic is low cost but affected by vapors, foam, and temp shifts. Use steering wheels or bridles to steady surfaces and allow maintenance without opening the vessel. Example: for crude oil tank with vapor and foam, choose guided wave radar with steering tube and configure dielectric setting for oil. Okay, we will continue in 15 minutes. Stay tuned. Thank you.